So good morning, ladies and gentlemen, or good evening or good afternoon, depending where you are. Here in Kiel we have morning. It's a pleasure now to give a short introduction into the activities of the chair in order to maybe start a cooperation with you and especially with Professor Kim. Okay. Well, I have three parts for the next couple of minutes. First, I would shortly introduce the research philosophy that we have here at the chair at the Christian-Albrechts-Universität zu Kiel in Germany. Then I have here three fields of research where we do research in. Don't be afraid, it's just one slide or two slides actually. And I want to close this short introduction to the chair with a little wrap up at the end. Okay, so let's start. So first, the research philosophy, and don't be afraid, it's just one slide about this topic. We do here research in engineering science, so actually two words, engineering and science, and I would shortly motivate what this means. Let's start with engineering. This means we do here signal and system theory and signal processing. And so system theory means that we work on systems that can be potentially used in real environments in practice. That's important because this means engineering in my perspective. This means also that we do the systems, or that we try to have real-time systems that operate in closed loops. Closed loops means you usually record something by means of microphones or hydrophones, for example, if it's underwater. You analyze the data very quickly, and then the signals that you send out, the transmitted signals, the loudspeaker signals, projector signals, they depend on what you have measured before, so the analysis of the measurement data. For example, in sonar applications, the sense signals might change, the duration might change, depending on what you have used there. In order that this works really quick, we usually go for minimum delay solutions. So quite often you could think about solutions that are very efficient in terms of numerical complexity, so reduce the number of multiplications and additions. Of course, that's also something that we do, but usually this beats the wish, or this counteracts with the wish that you would like to keep the delay at a minimum level. And over here we try to find a compromise that also always keeps the delay at a lowest possible part. Well, and then at the end, our solutions should work in practice in cooperation with industry quite often. So this means they should be numerically stable and robust, and also the computational, they should be computational and memory efficient. So try to reduce this as much as possible. And in order that they really work at the end, we don't only go for simulations, we really do field tests with systems that show their performance in real environments. You will see a couple of pictures where, for example, the sonar systems are actually used in the water, or if we have medical applications, then we usually have patients that test the systems. That's engineering. And our research, well, of course, we all do research. This means we do new things and hopefully innovative stuff in terms of hard and software. Since the chair is a signal processing chair, it's mainly about software. But of course, usually innovations come from both sides, and then we have cooperation partners. For example, when we look at new sensor principles, for example, a new type of magnetic sensor is investigated in the chair with a cooperation of other chairs. And then we have this cooperation. Because quite often a new type of sensor has advantages, of course, otherwise it will not be followed, but also disadvantages. And if you combine it with corresponding signal processing, you can lower the disadvantages and enhance the advantages. Usually we go then for adaptive and cognitive approaches. Adaptive is clear, self-adjusting in some sense. Cognitive means that you analyze your environment, and then for example, the send-out signals, loudspeaker signals, as I said, that they depend on what you have measured. And MIMO means usually that you have multiple input, multiple output. So a couple of hydrophones, a couple of EEG sensors, MEG sensors, and so on. And also the output signals are usually a multitude of outputs. And mainly our research comes from the measurement and the communication area. And that's enough for the research philosophy. It's just that you get a rough idea of which area is followed here in this, with this group. Okay, now the three fields of research. Well, we have here these three fields: underwater, medical, and speech and audio. So I have prepared one slide, one more detailed slide, or actually two for the last part. But shortly, what is underwater here? We usually work with cognitive MIMO sonar systems. MIMO in the sonar area means that each projector, each underwater loudspeaker sends out its own signal, its own individual signal that is orthogonal to each other. This is different to conventional beamforming, where you usually have time-delayed versions of one signal that you send out. This is quite interesting. It's quite often used in radar, but sonar is rather new with this kind of stuff. And the other thing is we try to transmit speech underwater, and then we have here a new mixed analog and digital mode. Quite often I think there was a time when everything goes from analog to digital. This is long ago, and this has clear benefits. But the underwater channel is a bit different. It's not that easy, and then this mixed mode is actually very interesting. Okay, medical applications. And this was the first part where I was not sure where to put one mode or one topic. Actually, here the last thing is that we try to improve the therapy of Parkinson, the speech or speaking therapy of Parkinson patients. And this is actually on one hand a medical topic, on the other hand a speech topic. So I wasn't sure where to put it, and then I decided to put it here under medical in this slide, but have a detailed slide because this is the part where I would like to cooperate with Professor Kim, and then show it in the speech part. We do research on magnetoelectric sensors. It's a special type of a magnetic sensor, and this sensor is actually able, or maybe able, to replace just simple electrodes as they are used in EEG or ECG, electrocardiography or electroencephalography, so heart or brain. And finally, we have speech and audio. This is where the origin of the chair is. I come from the German automotive industry, and therefore I have a lot of cooperations on automotive projects, mainly in the sense of speech enhancement. So a hands-free system, speech recognition system, especially the pre-processing part, and meanwhile also in-car communication systems, where you try to enhance also the communication within the passenger compartment. We do also automatic evaluation of these systems, and we try to have the same algorithms such as beamforming, feedback cancellation, and so on, that you use also for other applications, for example, as for breathing protection masks, or for communication units in breathing protection masks, as they are used by firefighters. Okay, let's dig a little bit into the first topic in underwater applications. So here you see a couple of pictures. Maybe we start with this little video that is played over here. So this shows our real-time system in the sense of a sonar simulator. So before we start, we have here a real-time simulator, a digital ocean, so to say. You can place their hydrophones and projectors and objects. And also, well, for example, the surface of the sea is actually moving a little bit, and this has also impact on noise, but also on reflections on the surface. And so first of all, we test our systems in a hardware in the loop approach, in the sense that really our sonar system gives the output signals to this digital ocean via an optical or an electrical interface. The sonar system has no knowledge whether we are really in the ocean or whether this digital ocean is used. And if we are, well, happy with the performance, then we actually go really in the sea, and it's not far from Kiel is at the Baltic Sea, so it's just a few hundred meters, and then we are at the Baltic Sea. Here you see a little ship of the chair. So there is a crane where we can put in the sonar systems. We have, well, not just one ship, and then you can put in here the projectors, and with the second ship, for example, the sensors, the hydrophones, we can do measurements. Here you see a couple of the projectors on this picture here. So these boxes are made for 16 channels, so we have a couple of them. The upper part here is the amplifier for the projectors. And then we have here two sound cards, AD and DA converter cards, one for the output and one for the input. And here the two PhDs are showing on two screens. One screen is actually for the sonar system and the other screen is for the digital ocean. And for example, you can place their objects, let them move, and you know the truth. This would be the upper monitor. And the lower one is actually used in the same fashion, where the system thinks where the objects are. And then you can simply compare them either in a visual inspection way or by really performing distance measures, and if you have this digital ocean active. Okay, and I think that's enough for the underwater application. Second thing is a medical application here. Let's dig there also a little bit deeper in. So here on this monitor you see here, well, first you might think it's an ECG signal, electrocardiography signal, but it's actually a magnetically measured one. So we can measure here with a multitude of channels and then solve inverse problems. For example, in order to know if there is a certain bridge of current that is flowing in the heart where it should not be. And this is, you measure, this is the, or you have an idea of the forward solution. So if there would, in the heart at a specific point, a current would flow, and then you can use field theory and then estimate what magnetic signals you would measure outside the human body. Forward solution, then you can really measure these signals and then try to invert the solution and then try to find the current density distribution in the heart, for example. And therefore you need these measurements. This is here a normal office, so to say, where we have this white chair. Currently it's a chair, but you can also lift it in order to become a bed and then lift it a bit higher. If you do measurements for a longer time, then it's actually nice to have, well, to work in a specific height, and then it's easier for you. And here we can put these magnetic sensors on the top of the heart in order to do some measurements. We compare this also with conventional magnetic measurements. For example, currently squids or OPMs are interesting sensors. OPM stands for optically pumped magnetometers. They can really measure with a better resolution, with lower noise as the sensors that we have here at the chair. But they need shielding. So they are here in a magnetically shielded chamber that we have at the chair. And these are the sensors that they put in order to do reference measurements. And the other sensors, they are made in cooperation with a whole CRC. CRC stands for Collaborative Research Center. This means about 30 or 40 PhD students are working on that field, and that in this area. Some of them come from the physics department, from the material science department, from engineering, but also from medical applications. And then we try to work together in order to, well, produce sensors that are as cheap as simple electrodes and as good as squids. At the moment, well, we are not as good as OPMs or squids, but we still work on it. And I'm not sure whether they will perform as good or not. Let's see, that's research. On the last picture, show me in a car. The idea was that we try to estimate where I would turn next, towards left or right or straight forward. And so I use here nearly no more than 200 channels EEG system, plus some sensors at electromyogram sensors at my arm, plus IMUs. And it was, we were able to predict about 200 milliseconds earlier where I would like to drive, left or right. So this has also security or well, issues, so to say. If you would know what the driver is doing, you can well compute whether this leads to a dangerous situation or not. Of course, no one would drive with such a setup, that's clear. After half an hour, all the electrodes become dry and then the contact is not as good as before. However, if we could replace this with magnetic sensors that really work in an automotive environment, and then it would be nice if you could predict where, which movement you want to do next as a driver. Okay, that is medical. And now finally to speech and audio, and that's actually the area where I would like to cooperate with Professor Kim and all of you, hopefully. So maybe this picture here shows where which problem the chair addresses at the beginning. I come from automotive industry, as I said before. I was with Harman, and then with companies that meanwhile belong to Nuance or Cerence, which is the automotive part of Nuance meanwhile. So if these two people drive in a car, and in Germany you can drive at really high speed, and then usually the backseat passenger, Anna here, she has problems to understand the front passenger. Both of them have been PhD students, so this is Jochen here. So what usually happens, the backseat passenger leans forward in order to make the distance between the source and the sink smaller. This improves, of course, the SNR. You can speak up, you can speak louder, and also you can turn your head. But this situation or this behavior is on one hand exhaustible because you have to speak up for a long period of time, and this is, well, not as nice. It's uncomfortable because of the seat position, and if the driver leans backwards and looks towards the rear passenger, then it has also safety issues. Well, and then you can, of course, record with microphones. For example, here's an array of microphones in this car, which was an S-Class here. So you can record, and you can use the loudspeakers that are installed in the car for playback, and then you can solve the problem with this. The problem is there is, of course, feedback. So if the loudspeakers are coupling back to the microphone, and then, well, with the gains that you need for getting an improvement, you are above the stability threshold. So, well, you need feedback cancellation, feedback suppression, beamforming, and the typical things that signal processing people in speech and audio would know about. Here is a car. This is a convertible. So in a convertible, it's even from the left to the right a problem. If you drive at, let's say, more than 70, 80, 90 kilometers per hour, and if you drive open, and it's pretty loud in these cars. And you can also solve this by, for example, microphones that are included in the security belt. This is a nice position, but it's moving all the time, so beamforming is not as easy. Well, all these systems, they will work later on embedded platforms, so on whatever DSPs and ARM processors. And our system, our real-time system, is able to predict about the complexity of an algorithm, whether it works or will not work on, for example, a TI or another DSP chip. So this is actually a very nice prediction. And this last picture shows now a Parkinson's speech therapy. Of course, this young lady here is not a Parkinson patient, but she was working on this in her well, university time. And this is also a PhD student. And so they make a speech recording now. This is a laptop where you see it from a medical view, so you can check parameters and see powers and pitch frequencies and so on. On the other side of this screen, there is a second monitor. So it's a monitor. It's a notebook with two monitors, both sides one, and she sees then, or this potential patient sees what you should do. And here you have a microphone array. This is not just for improving the speech quality in the sense that a couple of microphones are better than a single one. It's also because Parkinson people quite often don't speak loud enough. So therapy is quite often that they increase the loudness. And you can increase the loudness at the microphone by coming closer to it or by really speaking up. And these microphone array here is able to estimate on one hand where and which direction is this person speaking, and also from which distance is this person speaking. And then if she would come closer, the algorithms would realize this and then correct for it. So you really must speak up, and that's what the therapy is about, what you want to have. One more slide about it. We have also games. So for example, here you see a picture, so you can load pictures, and then you can cut these pictures into 9 or 12 or 16 pieces, and then it's randomized in some way. And the job is, for example, to reorder it, but with your voice. So for example, if you would like to have this part of the picture to move to the middle, and then you have to speak a loud A, and you can adjust, or the logopedic trained person can say, okay, how loud should it be? How long do you need to keep it stable? What about the variation of the pitch? How small or how large should it be? What about the power variation? If you would like to have this picture here to be moved down, you have to say an O, and the other one here an E, and so on. So I think it's clear. And therefore you can train to speak clearly and loudly vowels with this method. Or you can just record fluent speech. So you ask people to read, for example, certain passages, or you ask questions about whatever relatives or the well, what is in the fridge or something like this. And then you analyze, in this picture here, for example, only the voiced parts, and you extract the first and the second formant, so kind of resonance that you produce with your tongue and in this area when you speak. And then if you speak clearly, all the A's and U's and E's, they are far away from each other. And if you speak in a muffled voice, like if I speak like this, and then they all become closer and closer and closer. And so the area that is spanned with these centroids of these different vowels here, they become small, and this is a bad feature, or this is bad. And if it's large, this is good for a clear voice. And this is one of a couple of features that you can use in order to predict a so-called NTID score. This is a score that was at the beginning from 1 to 5 and at the end from 1 to 6. It's like a mark system in school, from very good to very bad, or very clearly understandable to not understandable at all. And the idea is that this is something that logopedic trained people would give as a mark, and we try to predict this, and this helps them to well, to check whether the therapy is good or not, or whether the patient has improved or not improved. And this is actually the area where I would like to cooperate, if possible, with Professor Kim. Okay, that's it from the fields of research. Forgive me if it was a bit longer, but I think you know this situation. If you speak about your own research, then you become really exhausted, or not exhausted, but you are happy about it. So sorry for being maybe a bit long. Okay, a very short wrap up now. So what was presented in this video, I started with very shortly the research philosophy, and then I was a bit longer about the 3 fields of research: underwater, speech and audio at the end, and medical in the middle. And I had some small details about Parkinson's speech analysis, because I think that this is one of the potential cooperation topics. And now I hope that the already started cooperation with Professor Kim could be deepened with this video, and that we come closer. I would be happy to come to Korea, maybe also with students, and also if Professor Kim or any other member of your faculty or students would come to Kiel, they are very welcome. Okay, that's it. Thank you very much for your attention, and bye-bye.